All right, so today we're going to finish up on conditionals. Before we continue on it, though, let's understand where we've been on conditionals. Remember that we have a basic if statement that allows you to specify a condition, a logical Boolean condition that is either true or false, and then that code will execute or it won't execute based on the truth value of that condition. Remember that we are on Piazza and YouTube, so if you have any questions, you can post there. But otherwise, you also have an if-else-if statement to provide an alternative. Either this code block gets executed or this code block gets executed. And then you can generalize that to as many conditions as you want, to as many statements as you want, with the else statement always being optional, right? You can use numerical comparison operators, but you can only use them for numbers. Any attempts to use them on, say, strings or something like that will lead to bad results, right? We went through several pitfalls, of course, and the way that you can get through those pitfalls is by using your GCC compiler as a linter. We'll talk about that more formally here in a second. But remember that you can't use conditions like this. You have to break them up with a logical AND condition. Make sure that you're not using assignment operators in your conditional statements. Make sure that you are well placing your semicolons, right? We also have a general negation operator. Anything can be negated by simply using the exclamation point. And then, of course, you can use Boolean variables. The best way to do that is to bring in a library to do it, stdbool. Then you can create Boolean variables that you can set to be true or false using the keywords true and false. You can combine logical statements by using the logical and the logical or operations, right? And then you can combine those in any using parentheses, negation operators to get any logical statement that you want. Right? You can also use these comparison operators. Like I said before, you can't use them with strings, but you can use them with single characters, right? You cannot use, say, equals equals with strings, but you can with single characters. Right? Why? What are single characters again? The ASCII text table, right? And in the ASCII text table, everything has a number. So capital A comes before capital B, and therefore you can treat them as numbers, right? Because they are all numbers in the ASCII text table, right? So let's go ahead and take a look at a quick example here that you'll see in your lab later today. If you want to prompt a user for input, right, you can ask them yes or no. So let's just go ahead and fake that by adding a Y here, right? Single quotes for single characters. And then you can check, was their response actually yes? If the input is equal to Y, right, then execute some command. Printf, you answered yes, right? Even though they only put in Y, right, and enter. All right, so will that work if it's lowercase? Are lowercase letters and uppercase letters the same? Nope, definitely not. So how could we do take care of this so that if they enter in a uppercase Y or a lowercase y, we'll take care of both of those instances? Yeah. An or statement, or the input is equal to a lowercase y. And in either one of those cases, they answered yes. Otherwise, suppose they entered N for no, right? Then they entered no. Or anything else, if they entered NQ because they didn't know what they were doing, right? Or they didn't listen to our yes or no, prompt for input, right? You answered something else, right? End the line. Okay? So you can use equals equals. You can even use less than or equal to if you want to. Did they answer with any letter that comes before or equal to capital Y? That doesn't make much sense though, right? But you can do that. Why? Because at the end of the day, characters are numbers because of the ASCII text table. Okay. I'll go ahead and put this in the notes so that you have it. But otherwise, another issue that you should be aware of is called short circuiting. So a lot of you are electrical engineers here. What is a short circuit? Well, what is a circuit, first of all? You're going from power to, say, light a lamp or something. Well, you can't just send power one way, right? It has to be in a circuit, right? Positive to negative or whatever. And then the electricity flowing through that circuit is what lights that light up, right? What happens when you short circuit it? Yeah. Right. If I took my fingers and I short circuited it, like put something across that circuit before it got to the light, electricity flows. It follows the path of least resistance. So it will short circuit in that shorter circuit back to the power source. Short circuiting is something very similar in code, right? So let me go ahead and ask you, consider the following logical statement. And I don't know what A and B are. Who cares, right? A and B. If A is false, does it matter what B is? What value B has? No. Why? Both have to be true for the entire thing to be true, right? Therefore, in the vast majority, in fact, all of them that I can think of, the vast majority of programming languages, B is not examined and or evaluated. It is short-circuited. Now, why is that? Think back 50 years when you measured computational cycles in seconds or in like tenths of a second or something like that. If you know, just looking at A, if you know the entire expression is going to be false, why would you waste your time looking at the second part, right? Exactly. Just go ahead and go on. Move on, right? And if you could save those CPU cycles, then you did it, because back then it really mattered. Now, nowadays, it doesn't really matter unless you're in an embedded system or something like that where you're still measuring CPU cycles in the macro level or whatever. But it's become to be known as an idiom, something that is a part of every language and expected to be there, right? No longer the case that it is necessary for efficiency, but programmers have come to expect it, expect this behavior. And so programming languages ever since C, in fact even before that, have implemented and relied on this short circuiting. Right? Here's the other example. Consider the following. Right? If I have A or B, right? If A is true, does it matter what B is? Nope. Likewise, B is not examined or evaluated. It is short-circuited. So those are the two instances, and then there are several combinations thereof. All right, if you start mixing these things around, but these two are the simplest ones to look at. So it short circuits. The second expression is not evaluated at all. Yeah. Question? Not problems, but idioms. So what are idioms in actual English? Yeah, metaphorical sayings that don't have their literal meaning, like raining cats and dogs, right? And in programming, since programming is a language, we have idioms as well. So let's go ahead and take a look at an example here. I'll go ahead and say if A is not null, right, and A is greater than 10, then do something, ... Now, we haven't talked about pointers yet, or nullity, but null values are nothing values. They don't have a 0 value, they don't have a 10 value, they don't have a 5 value, right? They don't have a value at all because they're null. What this is doing is it's asking, is A not null? If A is not null, then it's safe to examine. But if A is null, then making a comparison to 10 will result in a segmentation fault that you've witnessed before if you forget the ampersand or something like that, right? And we'll get to that later on in detail. But this is a common idiom. It's a nullity check. Is it safe to examine the value of A because it's not null? Now, short-circuiting, if we didn't have short-circuiting, both of these conditions would be evaluated, and if indeed A was null, then this one would end up being dangerous and resulting in a segmentation fault. But because we have short-circuiting, right, if A is null, then this first one is false, and the second one is never even executed. right? So it's a safety kind of thing. And you can rely on short circuiting to get you out of situations like that. Yeah?
When you say that it would be dangerous to do that, do you mean like the program would fail? Or
The program would fail as a segmentation fault, right? You would try, your program would be accessing memory that doesn't belong to you, and the operating system would kill it. Just like if you forget an ampersand with scanf, right? You get a segmentation fault. Hopefully you get a segmentation fault, right? So that's what it means that it's dangerous, right? That it would just result in undefined behavior, right? It's not going to blow up the computer or anything like that, right? No, of course not. Right. Nope. I mean, it should, unless your program is designed or you have a bad operating system where one program is able to take down all the others, then no, right? So remember, a lot of these things can be avoided by using your the full capacity of your GCC compiler. And we're going to be treating it as a linter, right? So code may be syntactically correct. Hopefully I spelled that right. In other words, it will compile, but may still contain bugs or errors, right? Lint are pieces of code that may look be okay, or they may look suspicious, right? And may lead to errors or not, right? In real life, lint, the little pieces on your clothes, right? That comes out of the dryer, so your clothes are clean, right? It's syntactically correct. It will compile, it will run. It may not even be an issue, right? Nobody even notices that little ball of lint over there, right? But sometimes lint can be a code smell, right? Okay, there's nothing wrong with it, but it smells fishy. So let's go ahead and take care of that. And you can use a linter, static analysis tools called linters. Linters are static analysis tools that can detect potential errors in your code before you compile it. That's what it means by static analysis. There's also dynamic analysis. Dynamic analysis is after you've compiled it and you're running it dynamically. Static generally means it looks at your code before you even compile it to see, oh, this might be a problem over here. And GCC can be used as a linter using the WALL flag. Right? This is warnings, detect or report all of them. Right? And it's the WALL flag, WALL. That's what it stands for. Okay. It's best practice to always compile with this flag so that you see those issues. Take care of all your compiler warnings. We don't. That is a design issue in your rubric for hacks. Make sure that you're taking care of all of your warnings because we do take off points for unresolved warnings. Right? We don't do that for labs because labs are based on completion. But when you run it through the grader, it says, as pre-testing commands or something like that. That's where it's actually compiling. And if you've got a bunch of errors, or not errors, but warnings, then you need to take care of those. Right? Usually it does mean that there's a bug. Yeah?
Will it say that when you submit it for grading if there are warnings?
Yep.
Okay.
And you can see the same exact warnings if you use the WALL flag. That's all we're doing, is we're running the WALL flag.
So if we don't see any errors come up on the
It should be okay, right? That doesn't mean it's bug-free. It could still crash, or you could get the wrong answers or something like that. That's why you got to look at all the output, right? And then go back and fix. Okay. All right, so let's go ahead and do an exercise to bring everything that we've done so far together. Right? And this exercise is going to be EE related, since half of you are EE majors. The other half of you will realize that if you do short circuit something, right, you put your hand in on a circuit, then what's going to happen? You get an electric shock, right? Now, if you're good about it, you make sure that you take precautions. What do you do if you're working with electricity? First of all, insulate yourself, or shut it off, right? Go down to the breakers. Now, that's the difference between an electrical engineer and an electrician, right? An electrical engineer will shut things off. An electrician will say, I'll worry about that later. Because we had an electrician come in and move our our outlets one time and said, I said, all right, I'm going to go downstairs and shut off the breakers. He said, nah, forget about that. I'm like, okay, whatever. It's your life, man. But not all electric shocks are the same, right? You can, in fact, there's a well-studied results on electrical shocks called the Dalziel scale. You might have seen this before. But based on the milliamps that actually go through human skin, right? It also depends on your gender. The one that I'm going to pull up here is for males. It's slightly, I think that it's slightly different for females, but it's basically almost the same. That between 0 and 1, there's no effect. You won't even feel it because that kind of amperage doesn't even break the human skin, right? But between 1 and 5.2 milliamperes, amperes, how do you guys pronounce it? Amperes, okay. Then you feel a slight sensation, right? Slight buzzing sensation, right? Kind of like putting your tongue, like a 9-volt battery to your tongue or something like that, right? And then you have pain from 5.2 to 62 milliamps. That's voluntary muscle control. In other words, you should still be able to pull yourself away from the circuit. This is why we never grab a wire or anything like that with a closed fist. Why? Because if it goes up to 62, 70 through 76 milliamps, you cannot voluntarily release it, right? You will be stuck to it until somebody comes along and kicks you off of the wire because you've lost control of your own muscles, all right? And you will hold on to that wire even though you shouldn't be, right? Then 76 to 90 is severe pain. After that, 90 to 100 is heart fibrillation, right? In other words, it interrupts the regular beat of your heart, and you may need to have those, shockers to get it back to square one, right? What happens after 500? I have no idea. That's all I wanted to go, right? Say what?
500 milliamps?
Yeah. Between 90 and 500 milliamps, you have heart fibrillation. Beyond that, I'm sure that you have heart fibrillation and severe burns, and your brain starts cooking, I'm sure. Yeah. Oh, yeah. Right. Yep. So be careful.
It goes through your skin, but most of the time your skin's fairly resistant.
Yeah. I mean, there's resistance. So 0 to 1, there's no effect because likely it's not going to even, go deep enough to do anything, right? Well, no, sorry. This is milliamps. So yeah, not even 1 amp. This is like half an amp?
Yes.
Yeah. I mean, it also depends on voltage too, I imagine. Because if it's low power, then it doesn't matter how many amps. But I'm not sure what the standard voltage on this scale is. This is just a scale that I took off of a safety diagram of some sort. Right? I don't know. This is just an exercise for conditional. So just be careful with your electricity. Right? I always shut off the breaker, so who cares? Yeah, just shut off the breaker, right? Or if it's a capacitor, what do? Discharge it, right? Make sure that you take a screwdriver and put it over the nodes on a capacitor and make sure that it's discharged, all right? And stand away. Wear a glove, maybe. Right? I don't know. All right, so let's go ahead and I'm going to go ahead and copy this demo to amps. There we go. And let's go ahead and edit that file instead. Come on. All right. It's not coming up. Oh, you know what? There, different course. There we go. Amps. Okay. Let's take that out. There we go. All right. So, first of all, we need to read the input from the user. Do we want to do this interactively or non-interactively? Which kind of practice do we want here? Remember, the interactively is going to be scanf. Non-interactively is going to be through the command line arguments, A2I or A2F. Which one do we want to do? Which one is in your hack? It's interactively, right? Scanf for hack 2 here, right? So do we want to do that? Okay. Printf, please enter the milliamps. Amps? Is that the shorthand for it? MA? The capital A? Okay. There we go. All right. We've prompted them to enter the milliamps. Then we use scanf. Of course, to do that, I need a variable. So should my milliamps, there's an okay variable name, MA, because electrical engineering, you would know it, right? If you're asking for milliamps, then that's the proper, that's the, what is that? This, the SI unit, right? The standard unit for it. But we can also go ahead and use milliamps, right? Just to be more descriptive. Now, should this be an integer? Or should this be probably a double? Why? Because you could have, you know, fractions of a milliamp. Right. Okay. Now we'll use scanf to read it in. If it's a double, what's my placeholder for a double using scanf? LF. Right. And I'll go ahead and use milliamps. There we go. Now, that's not correct, and you probably know why immediately because you've seen it before, but remember that if you use the wall flag, you can detect things like this. Amps and W, you know, if I just do it like this, okay, like this, it'll actually report it. But sometimes some setups won't, and you need the WAL flag here to actually report it. So what's wrong with my usage here? I need an ampersand in front of it. Again, magic symbol for now. Okay. All right, there I've got my milliamps. Now I want to check for what the effects are. Right? If it's 0 to 1, there's no effect. Right? So if milliamps is greater than 0, greater than or equal to 0, and milliamps is less than or equal to 1, then I'll print out that there's no effect. And the line. There we go. Is there a better way of writing that? I mean, I've got variable value. Yeah.
Couldn't you just do less than or equal to 1?
Okay, let's do that. What if milliamps is less than or equal to 1? Then there's no effect. Right. Okay, yeah.
You mean unless someone puts a negative value?
Yeah, what happens when somebody enters a negative value? Now, EE, folks, is there such thing as a negative milliamp? Yes. In what context?
Just flowing the other way.
Exactly. Yeah, so you could take the absolute value here and assume that negative 1 milliamp is just, you know, flowing in the other direction somehow, right? Or you could say, well, no, that's bad input. How do we want to design that? Design this program for that? We could go with absolute value, or we could say negative values are not allowed. Please try again and quit on them. Right? Which one do we want to do? Absolute value. Okay. In practice, you would have to go back to the stakeholders and say, what should we do in this case? Are we going to assume that negative values are okay? And if so, then how should we handle that? Right? And if they say, no, we shouldn't be allowing that for whatever business rules reasons, then you implement it like that. Right? All else fails, we'll go ahead and go with absolute value here. So milliamps is equal to absolute value. Well, here. Is this how milliamps? Is that how we do absolute value? No. I mean, that's mathematics, but this ain't mathematics, right? Is that how we do absolute value? It is if it's an integer. Is this an integer? Nope. What's going to end up happening if we have 0.5? It's going to truncate and give you 0. Fabs is what you want. And now that we're using the math library, we also now need to probably compile with what flag? -lm. Right? Great. So let's go ahead and test that. Negative, I don't know, 10. Oops, sorry, negative 10. All right. Uh-oh, it's not printing anything, right? Because we're not done yet, right? So let's go ahead and do that again, but with something that we have implemented so far. I don't know, negative 0.5, right? Milliamps. No effect. What other value should I try? Positive 0.5. 0, right? And 1. No effect. Right? So some edge cases there. You don't have to check every single possible value between -1 and +1. You can't, all right? They're an infinite number. Now, there aren't an infinite number, but there are a hell of a lot of them in this case there aren't infinite numbers because a computer is finite. It only has finite representation. but it has way too many to test, but that's good enough right there. Right? All right. I want to check for the next one where we've got, say, 1 to 5.2, which is a slight sensation. So if milliamps is greater than or equal to 1, and milliamps is less than, what was it, 5.2? Less than or equal to 5.2. Then printf, slight sensation, buzzing, slight sensation. There we go. Now, is that correct? Sure, but let's think about that for a second, right? Yeah, I'm duplicating the 1, right? Let's run this. What happens at 1? It will be no effect and a slight sensation. That's kind of a contradiction, right? It's one or the other. Yeah, if we want these to be mutually exclusive, first of all, we should do something like that. And so that only at 1 will it print no effect. Anything greater than 1 will print slight sensation. What's an even better solution? Else if, exactly. We want these to be mutually exclusive. We only want exactly one of these things to print, okay? And to do that, we need a series of if, else if, else if. Now this begs the question, right? This will actually fix the issue, right? If I go 1, it will be no effect and not slight sensation, even though I've got this greater than or equal to. Why? Because the first one gets evaluated true is the one that executes and not any others, okay? That's what it means by mutually exclusive. But this is kind of stupid. Why are you duplicating the logic here? All right, go ahead and get rid of that. And now it's strictly greater than 1, but less than or equal to 5.2. But do we even need this check right here? No, why? Yeah, if the first one if it's less than or equal to 1, the first one will execute. We know if we've gotten to this point to even look at this thing, at this condition, we know that it's greater than 1 already. Why write a lot of code when simple code does the trick, right? Make sure keep it simple, right? The KISS principle. Simpler engineering is generally always better engineering because there are fewer potential failure points. Right? All right, else if. Now I can go ahead and start copy pasting the rest of it, right? Else if, in fact, I'm going to do just that. Else if, blah blah. And what's the next one? 62, right? So 62, and it's going to be pain, voluntary muscle control. I will go ahead and copy that. Pain, voluntary muscle control. You still retain it is what that means, right? Otherwise, the next one, and it's 76 and 90. So 76 and 90 was what? Severe pain, et cetera, right? And then one more cut and paste for 90 to 500 would be heart fibrillation. I don't know how to spell that. There we go. Correct? Yeah, what did I do? Copy pasta, copy pasta, copy pasta. Right? That leads inevitably to at least one bug. Right? Now in this case it was intentional. Hopefully you saw what that bug was. I copy pasted, but I didn't change. Pain, voluntary muscle control, pain, voluntary muscle control. What is it? Actually loss of control. Right? So fix that. Make sure that you are either being extremely diligent or that you're not getting in the habit of copy pasta, copy pasta, copy pasta. Right? Okay, let's execute that and let's test some things. Maybe, I don't know, 50. What would I expect for 50 milliamps? Pain, voluntary muscle control is retained, right? You can still let go, right? Typically if you touch the residential outlet or something, right? That's why if you do need the poor man's tester, what are those testers called? Oh, yes, a fork. What is it? And that's not an altimeter. voltmeter, voltimeter, or whatever they're called, right? You put that to that, and you find, oh yes, this is a live wire, right? But if you absolutely have to do it, not a fork, but you put the back of your hand to it, right? Why? Because then you can still have muscle control and you can pull it away, right? But don't even do that, and don't do a fork either. All right. No, definitely don't do that, right? So let's test another one. What if it's, say, 90? 90, I would expect what? Heart fibrillation? Severe pain, right? Let's go back to our table here. What's one thing that was unclear about this table? Yeah, what? Well, that too. Hold on to that thought. But it says 62 to 76, but then also 76 to 90. What happens exactly at 76? What happens exactly at 90? Right? That's one of those things where you have to go back and you have to ask for clarification from whoever wrote the specifications. That's why there's an engineering phase to design of design specifications or requirement solicitation. Right? You have to absolutely make sure that everything is well defined. Because if you have ambiguous instructions like this, 90, what happens at 90, right? And then any old programmer is allowed to decide what the hell happens in that situation, right? You don't want that to happen. If it's a bad design, if it's a bad specification, you need to go back and get clarification. Right? What happens when it's 90? What happens when it's 76? Right? What happens on those corner cases? Yeah. Yeah.
But changing the other one to just greater than.
Okay. I like that. Less than or equal to. Well, we have less than or equal to, less than or equal to, less than or equal to. So by default here, we're saying that the high end goes with the lower end, the lower one, right? And that's what we ended up programming, right? Now, is that okay? You got to go ask the people that are paying for it, right? The stakeholders. And if that's if they say yes, great, go ahead and do it. If they don't get back to you, that's what contracts are for, right? Well, you gave us bad specifications. It doesn't matter that they were bad specifications. Our implementation was to the specification, so pay me. That's it. Yeah. You could, and then that would default the corner cases to the upper end, right? So if you did it like this, oops. Now 90 is going to be what? Oh, sure. Now 90 is going to be, before it was severe pain, but now it is heart fibrillation. Again, I did this intentionally ambiguous so that we could have that discussion point of what specifications are. And that's what engineering is all about, right? Well, you told us that we could build that bridge with this kind of steel and this kind of concrete, and it collapsed. Well, it wasn't our problem. It was whoever said this, that you could do that in the first place, right? That's why there is an entire chain of specifications and sign-offs on most engineering disciplines, right? You have to have a certified engineer that signs off on these on this design phase, on this blueprint, on this whatever, right? And if it falls through, then you have that entire chain to go back on. This person failed at that point, right? Now the other question is, what happens at above 500? Do I have a catch-all default value here? Nope. Else, I don't know what happens, right? Something happens. ... What? That's when you have to again go back to your stakeholders and say, all right, you didn't say what happens at 500, right? Oh, okay, well, what happens at 500 or above is death or something, right? Guaranteed death, right? Something happened. I don't know. Something bad. Something, all right, bad happens.
How are you typing right now?
Oh, yeah, that's a good point. And now it's a ghost in the machine. And let's test it. What if I do 1,000? Right? Something bad happens, right? What if I just mashed the keyboard and said hello? Right? What's going to happen here? Same thing happens. It's going to end up evaluating a 0, right? Because H, that's no number I've ever heard of, so no effect, right? Why? Because it ended up being milliamps. If you want to, you can be a little bit more verbose, right? You could say that printf %f milliamps is ... and the line, or no, we won't even end the line. We'll just go ahead and go with that, and then print out milliamps. Right? This is kind of a sanity check. Did they actually enter in something correctly? Hello? And it's actually saying, well, 0, that's kind of what you entered, is no effect. Right? Yeah?
Couldn't you have a check on that?
You could. That gets into a little bit more deeply on how scanf works. Man pages, scanf. Scanf also returns an integer, the number of tokens that it matched. So I'll show that to you, but we're not expecting you to do it because we're going to be getting away almost immediately from interactive input here. Int, I don't know, num tokens. Right? So what is a token? A token is kind of a coin, right? Or a token is like a conch shell that allows you to speak, right? You take now you've got the gavel, you can speak, right? A token is this thing right here. Was the placeholder actually matched? And we can check for that. If num tokens is 1, then that means that they actually entered in a valid number. And so we can go on. Otherwise, if it's not equal to 1, then we know that they mashed the keyboard and said hello, right? Or something like that. Printf, error, please try again. End the line, and we'll go ahead and exit and kill the entire program on them. Right? Hello? Right? Error, please try again. Right? It didn't read any valid tokens out of that. Whereas if I had put in, like, say, 10 milliamps, then it's paying voluntary muscle control. Right? That's how you can take care of it, but we're not expecting that in any of your hacks or anything. Right? If you wanted to, you could go into, say, a loop and ask them again. Right? To do, maybe replace this with a loop that re-prompts them for valid input. ... To do that, we're going to have to cover loops, which coincidentally we're doing now, right, in a second. Right? Before, any questions on conditionals or this exercise? No? All right, well, I'll go ahead and make sure that you've got this in the notes. And we'll come back to it and maybe as a demonstration, but maybe by the end of the day, discuss how we could do that, do this to-do here with a loop. By the way, that's a very common programmer's trick, right? Put in a comment that I need to do this as a reminder to myself that there's this thing I need to do, but I don't want to do it right now because I'm lazy or I want to go get some lunch or something like that. If you put in a comment, a to-do, all caps here, that's a common way of noting to yourself that there's something that has to be done. And in a lot of IDEs, and not this one though, maybe under problems, nope. In a lot of IDEs, it will actually go through your code and it will detect these to-dos and it will gather them in a task list. And then you have a task list where you can double click on this and it takes you to, okay, now I'm full, I had my lunch, right? I had my coffee or whatever, now I'm ready to sit down and start taking care of these things. You can go to your task list and then jump to each one individually. Right? This one, unfortunately, doesn't support that. Probably the full version of VS Code does, though, I would imagine. Right? Oh, does it? In the desktop version, you mean? Yeah. Okay. Yeah, it'll mark it up somehow. Like, you need to take care of this, right? All right. We'll take care of it later because I don't want to do it right now, right? In true programmer fashion. Right? What's the whole point of programming anyway? To do the laziest thing possible, right? That's why you want to program stuff, so that you automate stuff and not have to do it, right? In fact, there's an XKCD on it. XKCD automation chart. There we go. When does it pay to actually write a program to do something, right? Oh, no, this is not it. What is it? Which one is it? What should I search for? When to program to save time? I don't know. Is it worth the time? There we go. All right. So, how much time did you shave off? If it's only 1 second and you only do it only do it once a year, right? Then don't bother automating it. But if you do it 50 times a day and it takes you 1 second every day, maybe then you have an argument to, that you want to automate that, right? If it takes you a full day and you do it 50 times a day, well, that's not possible. That's why it's blanked out. But if you do it 50 times a day and it's 5 minutes a day, then by automating that process, you've saved 9 months, right? So when you do an analysis like this, you think, is it worth it, right? There's still things on this course that I could automate away, and I don't just because I've done the analysis and it's not worth my time, right? One thing that is quickly becoming worth my time to automate away is the lab grading, though, right? And that's my next task. I have to manually grade all that stuff on Wednesdays. Right? That's why sometimes you'll see your grade, and then I have to go to class, and I have to do other things, and I come back to it later that night and take care of it, right? So, loops, right? We need a way to repeatedly execute some piece of code, right? There are 4 basic elements to a loop control structure. An initialization statement. In other words, if you're going to loop around and do something, right? If you're going to run around an oval racetrack, right? You have to start somewhere, right? So the starting point. That's the initialization. That's where the loop starts. A continuation condition. As you're running around this big oval, right? As the coach told you that you've run enough laps, right? And no, okay, well, there's 1 lap. Nope, you need to do 10 laps. Okay, continue. Do 1 more lap. You've only done 2 so far. Have you done all the 10 required laps? Nope, keep going, right? You need a continuation condition, or the opposite of that is a termination condition. When you hit those 10 laps, right, then that's when you can stop. That's when you terminate the loop and you jump out of the loop and continue with the rest of the code. Right? You also have to have an increment or an update statement that makes progress towards that termination condition, right? Each time that you go around the racetrack, you need to increment, I've done 1 lap, I've done 2 laps, I've done 3 laps, right? Otherwise, if you go around and you never count the actual number of laps that you're going, are you ever going to stop running? Nope, the coach just keeps saying, go on, do more, right? And maybe that's how they actually do it. I don't know. I was never on the track team. Then, of course, you need to be doing something in your loop. That's the 4th thing. You need a loop body, the code that executes for every iteration of that loop. So let's come back over here and let's take a look at this demo. And let's write we'll talk about the syntax in detail here, but I'm going to write 2 loops here. One's called a for loop, and the other that I'll do in here in a second is a while loop. For int I equals 0, I is less than, say, 10, I plus plus. Right? And I'll print out printf lap number %d and the line, and we'll print out I. Right? Now let me go ahead and compile this demo. Right, there we go, and run it. Let's observe what it looks like. So I've got lap number 0, then lap number 1, then lap number 2, 3, 4, 5, 6, 7, 8, all the way up to 9. Right? Now, normally, if you're counting on your fingers, you start counting at 1, right? But that's what normal people do. We're computer scientists. We always start our counting, regardless of what it is, at 0, and we'll understand why when we take a look at arrays later on. Right? But you can see how we started that, right? We've got this integer I, and we initialize it to 0, and that's why we have lap 0. I print it out. Is I less than or equal is strictly less than 10? Yes. Then the entire loop body here gets executed. At the end of the loop, we update our I to be I++. That's shorthand syntax for add 1 to I. So I starts at 0, then it goes to 1, 2, 3, 4, 5, all the way up to 9, right? When it prints 9 here. Is 9 less than or less than 10? Yep. So it ends up printing I is 9. And then I increments to 10. Is 10 less than 10? Nope. That's why we don't see a lap 10 down here. Right? When this is no longer true, we break out of the for loop and return go back to regular control flow down here. Done. There we go. So let's see that in action and run it. Now, to understand this a little bit better, I'm going to visualize it using a tool called Python Tutor. Don't worry, it's not about Python. It's got a C mode over here. Hopefully it's still up. There we go. I'm going to take this code, and I'm going to visualize its execution. There we go. All right, let's step through this step by step. Right? We're going to go ahead and set up our variable I here. Right here, it's uninitialized. So what happens on the first iteration of this loop is it gets initialized to 0. Right? Let me go ahead and zoom in. There we go. All right. Now I is less than 10, so lap 0 ends up getting printed. Right? Now what happens next? This I++ gets executed, and it becomes 1. Do you see that over here? It changed to 1. I can go ahead and step through this, and for each iteration of the loop, you see that it gets incremented. When does it get incremented? After or before the print statement? So here's the print statement, print 3. Right? At the end of the loop is when this I++ occurs. Right? It goes to 4. Then it goes back to the print statement, ... until 9. Right? And then it breaks out of that for loop and prints done at the very end. Right? You can use this if you want to. The link is available in Canvas. Otherwise, it's pythontutor.com, and you can go to the C mode and compile any C code and walk through it. All right? Okay. Here's an alternative. Here's the exact same thing with another loop called a while loop. Right? It's called a while loop. Why? Because we use the keyword while. Right? Now, this one's a little bit different. We create the variable before the while loop and initialize it before the while loop. Up here, we did it within the loop. We have 3 constructs over here with our for loop. While I is less than 10, we go ahead and printf. Well, here, I'm just going to steal this code. There we go. There. Now, predict how this is going to go. I is initially 0. Right? While I is strictly less than 10, print it out. Right? Do you see that I++ anywhere like you saw with the for loop up here? No. What's going to happen? Okay. It's going to run and run and run. I like that. This is called an infinite loop, right? It won't eventually crash. It'll just keep doing nothing, right? This will go until something external happens to it, right? So second law of thermodynamics, right? It's going to be preserved until acted upon by an external force. That external force is going to be me, right? I killed it. How did I kill that program? Control C, right? To do an equivalent loop here, we're going to have to do that I++ ourselves, right there. So after we've printed it, we will go ahead and print this out, and then done for a second time. Oops. Compile that, run it, and you'll see that there's the first for loop, 0 through 9. There's the while loop, 0 through 9, and they're equivalent loops. We'll talk about why we have two loop control structures. We actually have 3 in C. We won't cover the third, a do while loop. But we'll talk about the appropriate times to use each one of these. What if I instead did it up here, I++ before I printed? What's the output going to be now? Let's walk through it. 0. Is 0 strictly less than 10? Yep. So we increment it by 1. What do we end up getting what ends up getting printed first then? 1, lap 1. What ends up getting printed last? 10. Why is that? Fast forward, fast forward, fast forward. Suppose that we've got I is 9, right? 9 is strictly less than 10. We increment 9 to 10, and that's what gets printed at last, right? We come up here, and 10, is 10 strictly less than 10? Nope. That's when we break out and we print done. Okay. So there are your 2 idiomatic loops, right? These are just basic loops. Right? We actually want them to do something though, right? And to do that, we need to understand their syntax a little bit better. Okay. I'll go ahead and put that URL for the Python tutor in the notes, so you don't have to go searching for it, but it is in Canvas already. So we've got for loops, And the three main parts, the initialization, the continuation, and the increment, they're all done within the same line, right? Let's go ahead and go back up to our for loop. Oh, yeah, I'll get rid of all this here. So here's the initialization condition. Here's the continuation condition. As long as this is true, it will execute one more time. And then here's our increment condition towards that termination condition, right? So the three main parts, initialization, continuation, and increment, are all in the same line. The loop will continue to execute. Another iteration is what we call it. Iteration. There we go. As long as the continuation condition evaluates to true. Right? The continuation condition is evaluated at the start of an iteration, right? Not at the end. Right? That's the other loop, the do-while loop that we won't cover. Okay. The increment is executed at the end of an iteration. Right? The initialization is only ever executed once before the loop begins. So it is possible that you have 0 iterations. For example, what if I started over here at, I won't start at 0, what if I started at 100? Will this end up printing anything? No, why? We immediately start at 100. Is 100 less than, strictly less than 10? No. No iteration at all. Right? You can have empty loops if you want to. Right? The syntax, of course, should be clear. Why do we call it a for loop? We use the keyword for, right? Who would have thunk, right? Note where semicolons are. Semicolons end the initialization and continuation statements, but not the iteration. And that's weird, right? And I agree that it's weird. Don't ask me why they did it that way. This is indeed an executable statement. If you really wanted to be consistent, it should have been like this. But it ain't. This will not compile, right? Don't ask me why. That's stupid. I agree, right? The semicolons only end the initialization and the continuation, not the increment, right? Again, why?
Will that raise a warning starting I at 100 and then
Nope. Proof. At least I don't think so. It'd be very, very smart compiler to seek that out, right? That it's dead code, but no. Right? Now you could do maybe some deeper analysis, so some more sophisticated tool that would detect something like that. You could do maybe a dynamic analysis that would detect something like that. But I mean, static analyzer and tools don't usually detect something like that because that's stupid. Why would anybody do that to begin with, right? They assume a minimum level of competence to begin with, right? Again, this is just for demonstration purposes, right? Okay? So not the iteration. Note that the iteration variable, I, is declared within the loop structure, right? Therefore, it's the scope of I is limited to the for loop itself. Right? All right, that's the modern way of doing it. If you go back in time to old school C, like even before 1990, right? That's ancient, right? You could not do that. You would have to do something like this, int I. Right? And then you can go ahead and set I to 0, ... That means that I will exist after the for loop. Printf, I after the for loop is %d and line I. Right? This is old C, right? At least 30 years ago. I after the loop is 10 because we broke out of the loop, right? Don't do that, right? We are now 30 years into the future past 1990. We can afford loop scoped variable control structures, right? But prior to like 1990, or depending on your setup as well, if your standard is like C89 or prior to that, then you would not be able to do something like this. But because we are able to do something like this, this variable I only exists between lines 8 and 10. Will I be able to print I out after the for loop is done if it's out of scope? Nope. In fact, it won't even compile. I is undeclared. It doesn't know anything about I on lines 13. Right? I does not exist down there. It only existed for this for loop up here. Right? So keep that in mind. It only exists for the loop itself when you do it like that, when you do it proper. Right? Some new syntax here. New syntax. I++ adds 1 to the variable I. Well, we also have some other other new syntax, right? You can extend that, and what if I do I minus minus? It subtracts 1. Subtracts 1 from the variable I. Right? You can also do compound assignments. Right? So, for example, you can do something like this. I is equal to I plus 10. Right? Can be rewritten as I plus equals 10. Right? So if you want to add 10, 10, 20, 30, 40 to your index variable here, or your iteration variable, that's why I'm using I as an iteration variable, I for iteration, right? If you want to add 10, what you can do is you can shorthand it. This will automatically add 10 to the variable I. Right? If you want to do something other than just adding 1 or subtracting 1. Likewise, you can do it with subtraction. I is equal to I minus 5, right? Can be rewritten as I minus equals 5. There we go. There. You can also do it with multiplication and division. I is equal to I times 2. In other words, we're doubling it. Can be rewritten as I times equals 2. Now, what happens when you do it with division, though? I is equal to I divided by 2. So 10 divided by 2 is going to be what? 5, right? 11 divided by 2 is going to be what? 5. Why? 5.5, truncation, that 0.5 gets thrown away, right? So this is integer division, right? Can be rewritten as I divide equal to. And it doesn't have to be 2. It can be any other constant. It can also be an expression, I believe. But don't get fancy, right? Keep it simple so that you don't have to worry about that stuff, right? Okay. Any questions on that new syntax? So why do we have this new syntax? This, again, is an idiom, right? That if you always had to write it out full, like I is equal to I plus 1, I is equal to I plus 1, right? That's really long. This is a shorthand way of doing that. If you just want to add 1, just go ahead and go plus plus, right? That's what we call syntactic sugar. Right? So if you eat your oatmeal, yeah, oatmeal's fine. But what do you do to your oatmeal or your cereal or whatever to make it taste better? You add milk, okay? What else do you add? Sugar, right? Sugar so that you now have frosted flakes instead of just regular old corn flakes. Right? And that's what we like in our languages, too. Imagine if English were stripped down to its bare essentials. You wouldn't have 50 different adjectives to describe good or cool or whatever, right? We like our languages to be, expressive. We like our languages to be flexible. And so that's what syntactic sugar does. It adds flexibility. It adds shorthand stuff to languages. Not all languages do this, right? Python, for example, you can do this in Python, right? You can have the compound assignment operator, but anybody have any Python experience? Can you do this in Python? Nope. Why not? Because they're stubborn, and we don't want to be like those C folks, right? We want to make sure that there are things that you can't do in our languages that you can do in other languages. It's kind of stupid, right? But in any case, not all languages support this, right? Another one that had it and then they took it out, I think, was Swift, but don't quote me on that. Swift is the programming language of choice for what? iOS programming. So if you need to do an Apple phone app or a Mac app or something like that, you're probably going to be doing it in Swift. Right? Okay. while loops. Right? While loops are different in that they will use what? Keyword while. Good. It's obvious, right? So let me go ahead and give the, well, here, I got rid of the old syntax, so let me go ahead and just give this one to you. This is a little bit different, right? We have the same basic 4 parts, the initialization, the continuation, the iteration, and the loop body, but they're not all on the same line anymore. The initialization happens before the while loop. Right? The continuation happens in the parentheses next to the while loop. The loop body, that's the same, right? It's opening curly bracket, closing curly bracket. But the continuation condition here is a little bit more flexible. You can put it at the end of the loop, or you can put it at the beginning of the loop, right? Your choice. Whereas with a for loop, you have no choice. It's always going to be at the end of the loop, right? So the differences, key differences. Right? The initialization happens before the loop. One consequence is that you cannot have a loop scoped variable. Right? So remember up here with this example, right? I only exists for this for loop. You can't do that with a while loop. This is not possible. You can't say while int I is less than or equal to 10. Right? It doesn't make syntactic sense. You can't do that. So that's a consequence of using a while loop. You are making the decision that this variable I is going to have to live after the while loop as well. Right? Another difference is that you have flexibility on where the increment occurs. Right? You have to specify it in the loop body. Right? And you can put it at the top, you can put it at the bottom. What are the consequences of that? Let me go ahead and cut and paste this and try it out. There we go. There. So what if I put it at the end of the loop? Predict what this is going to print out. All right, so we started at 1. Careful, this is different than what we did before. We started at 1. So is I less than or equal to 10? Yep. What gets printed first then? 1. And then it increments to 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 is less than or equal to 10. So we end up printing 10. Do we end up printing 11? Nope. But the loop variable does exist after that. I still exists and has a value of %d and the line I. What's its value going to be after that loop? 11, because we broke out of the loop. Right? Now what happens when I change it so that it increments above instead? The first thing. Yeah.
You would add 1 before it prints the variable, so it print 2 to start with.
So it'll start at 2. Where will it end? 11?
It should still end at 10.
Let's find out. Now it ends at 11. Let's find out why. Right? So I is less than 10, I is now 10. 10 is less than or equal to 10. We come in and increment it immediately to 11, and I've run out of fingers. Right? It prints 11, and because it's done at the beginning, 11 is not less than or equal to 10, so we immediately break out of this while loop, going down to the print statement. Right? And it still retains its value of 11. This will, as you're beginning, right, this will drive you crazy because you'll have off by 1 errors all the time. Right? That you're starting too late. You're starting 1 increment, you're starting 1 iteration late, or you're going 1 iteration too many. Right? So make sure that you are aware of the nuances of both of these loops. Right? All right. So when do you do one and when do you do the other? Well, we'll save that for next time. Actually, I do like to show this though. Does anybody know what a zune is? All right. Oh, okay. Tell me what a zune is. Good. It's an MP3 player.
It's an MP3 player shaped like a soccer ball.
A what? Oh, you can still download the software for it.
Failed it.
Here we go. All right, there. The Zune was a Microsoft competitor to the iPod, excuse me, right? and it was the first generation that had the video stuff on it. It was not a touch screen, by the way. Neither was the iPod, the early generation iPods. It had a radio in it. So if you still wanted to listen to your MP3s and listen to the radio, the Zune was your choice. And it was also about $100 cheaper, right? So why it failed, well, I don't know. You get what you pay for. Because on December 31st, 2008, every Zune in the world froze for exactly 24 hours. Why? 2008 was a leap year. The following code was later found to be in a subsystem, not by Microsoft, by one of its subsystem contractors or whatever, right? Let's examine that Zune bug. This is the actual code. It was published as after the fact. So it's 2008. It's December 31st. December 31st, and a leap year is going to be the 366th day of the year, right? Because there are 366 days in a leap year, February 29th. So days was 366, which is strictly greater than 365. We detect, so in other words, we're at the end of the year. We have this function that says, is it a leap year? Well, 2008 was a leap year, so this evaluates to true. Now, what this code is trying to do is it's trying to subtract 366 to start over at January 1st and add 1 to the year. Right? So we're going to start off at day 0 or whatever it is. Okay? So 2008 is a leap year, so this code takes over. What was days again? 366. Remember, it's a leap year. Is that strictly greater than 366? Nope. There is no else condition, so where do we go? All the way back up to the while loop. Did we change days? Nope, it's still 366. So this is true. It's still a leap year because we didn't make any changes, right? 366 is still strictly not strictly greater than 366. And so what happens? We come back up to the while loop. We're stuck not in an infinite loop, because what happens on 24 hours later? Now days is 367, right? So that is strictly greater than 366. This executes, and suddenly your Zune starts working 24 hours later, right?
How did they miss this?
Exactly. How did they miss this? They didn't do proper testing, right? How are we testing this amps over here? We were testing multiple test cases. We were testing edge cases. What happens at 62? What happens when we throw at something that was unexpected, like some negative milliamps, right? We were testing this as we went along, right? And we were testing every single possible, not every single possible, but enough test cases to have high confidence that this actually works. What obviously did they never test? The last day of a leap year. Maybe the first day of a leap year. Maybe a good test would have been in the middle, in June sometime of a leap year, right? Setting these tests up and making sure that it runs is extremely important. And that's what you're going to be start doing some informal unit testing in your lab today with this exercise. Is it a leap year or not, right?
I just don't know why they even use greater than in the first place.
That would be the fix. It should be greater than or equal to, right? It was a bug. It was a
It's
bug.
like, how would it be more than 366?
Well, 300 if it's
A super leap year just
yeah, super leap year, sure. Well, I mean they do change time from time to time, right? Are we on the Gregorian calendar? Yeah, it wasn't always the Gregorian calendar, right? In fact, some countries still have different calendars tied to like emperors' reigns and stuff like that, right? In fact, we might be ending daylight savings time in this country, maybe if the Senate has passed it, but the House has not. Right? It's still yet to be decided. Right?
I think it's
So time can change, right? All right, I'll see you in your lab there.